Okay, we seem to be live. Okay, good. So today is going to be the last lecture on zero knowledge protocols. Uh, and I mean, technically speaking, this entire topic was something that is usually not covered in an introductory complexity course. And the reason I'm covering it is primarily twofold, as I mentioned on Academy. One is I just think it's a really cool topic. And the second is also, I think this is like in most cases, I mean, you get more comfortable with it once you become familiar. And it's quite understandable that maybe the first time you encounter it is something that it seems a little counterintuitive or something. But hopefully this is I mean, in this current era where we have things like Academy and so on. I mean, if you have any questions, please keep asking on the questions, and I'll try to keep giving you as many examples as I can, so that hopefully at some point you just get more comfortable with this thing, and then you are at a position to appreciate it. And also, if you are going to be someone who starts working in an area like crypto or something, zero knowledge is a very, very important part there. So hopefully it enables you, I mean, if that's a path that you're going to go through. Okay, so today we're going to look at a result that we mentioned very briefly last time, which is the fact that can you convert any interactive protocol into a zero knowledge protocol? Okay, so that's we're going to spend some time, but as we'll see, the proof will be surprisingly, or at least the idea of the proof will be surprisingly short. Okay, and one needs to work out the details, but I mean, building up on the result of Goldreich, Mikali, Wigderson, it's a very clever but short step. I mean, it's like super clever, but it's a short step from there. And then I'll just introduce something which is called proofs of knowledge. Okay, again a very different. It's a weird notion which seems very, very intuitive, but defining it took a while. In fact, they were actually so the the final definition. I mean, as we'll see, was actually a way of, there were many different definitions that were there in literature which were not ideal for certain reasons, and Bellare and Goldreich actually wrote a paper to properly define what proofs of knowledge were, and pointing out what are the issues with the previous definition, etc. So these are concepts that seem like they're intuitive, and these are things that seem interesting, but actually writing down the definition is really where the creativity of this goes. I mean, to be able to formalize a notion of this sort about what does it mean to say a person knows something, and to somehow try and formalize it. So we'll do these two things, and uh, but I'll just reassure people that for the subsequent lectures, etc., you don't really need zero knowledge. So if things, I mean, if you feel this is something that's getting a little hairy or something, I mean, don't worry too much about it. But please feel free to ask questions on Academy and so on, and I'll answer as many of them as possible. Keep giving you examples, uh, and and hopefully at some point it becomes easier. Okay, so so let's do a recap, and this recap is going to be a long recap because I'm more or less going to condense what we did in the last lecture uh, and go over everything. So we defined what zero knowledge was. A protocol, a language is said to have a zero knowledge interactive protocol if firstly it must have a legitimate interactive protocol, and that would mean that the interactive protocol must involve some completeness and soundness conditions. And completeness, just to recall, is that whenever you have a yes instance, that is, you're dealing with strings in the language, then the conversation, I mean, the intended conversation. By that I mean, if the verifier acts as he is like designed to, and if the prover acts as the prover is designed to, then that conversation will result in the verifier accepting with decent probability. We can fret about what exactly this 2/3 must be, but anyway, you want this to happen with high probability. And on the other hand, you want to sort of guard against people who might try to deceive you in the no instances. So there you want to say that no matter what the prover does, this prover could be all powerful. I mean, you can actively try to make sure that the verifier is actually going to accept, even though the verifier should not be accepting. You want to say that the conversation is somehow built in such a way that it guards the verifier against potentially dishonest provers. So the chance of the verifier accepting is at most 1/3. Again, this can be driven down if necessary. If your 1/3 is not good enough guarantees for you, you can drive this down. And then the third part, which was the zero knowledge part of it, and this is about what the verifier learns from the protocol. Okay, and this was defined as follows to basically say that whatever everything that the verifier learned is basically what happens in the view. What is the verifier view of a conversation? So this may involve some random coins that the verifier tosses. What was the message that he sent to the prover? What was the message that the prover replied back, etc. The transcript along with the local random coin tosses, etc. But there is a simulator which has absolutely no access to the prover at all. This simulator is just essentially a polynomial time machine. Okay, it's a randomized expected polynomial time machine, but it's basically something that the verifier could have run on verifier side itself, which has the ability of giving you a sample of a potential conversation between the verifier and the prover. Okay, so so in some sense, I mean, the one thing that I want to stress, I think this came up in Academy a lot. Notice that the point of the simulator is just to give you the entire transcript. So the simulator could do something crazy, like first sample the last message and then sample the message before that, etc., etc. But a conversation with the prover has to go in some sequential fashion. So often a conversation with the prover will be like the prover says something, then you ask the prover for a challenge, and then the prover gives a response or something of that sort. But the simulator has the ability of first generating the response and then generating the challenge and something else and so on. So the job of the simulator is just to give you the entire transcript and not in sequential order. But a prover is supposed to convince a verifier by somehow slowly revealing what the transcript is. Okay, and I mean, I think these are things that only when you see a bunch of examples and you try out this for a few things does it sort of really sink in as to why the simulator definition exactly captures what it means to say the verifier learned nothing. Okay, because you're basically saying that the conversation with the prover just gave you a sample from this distribution, but this is a distribution I could have given you anyway. So what's the point of you talking to the prover? So that's in some sense that's the content of what the zero knowledge part is. Okay.
So RP.
Yeah.
So even zero knowledge has to be only for X belongs to L.
Oh yeah. So okay, good. I should have maybe added. Uh, that is, this is only for X is in L. Okay. I mean, otherwise, I mean, you don't care anyway. The verifier is not really. I mean, the prover. the, okay. Okay. I'm trying to figure out how do I justify this fact. I mean, but yeah, but I agree with you that the conversation with the honest prover makes sense only when you are talking about yes instances.
So you sort of think of it this way: soundness, you're protecting the verifier from malicious provers.
Yeah.
Zero knowledge, you're protecting the
honest prover
from malicious verifiers.
Yeah, the honest prover when X was not in L would have maybe started off the conversation between, hey, I can't convince you. I mean, because I'm trying to prove a wrong statement or something of that sort. Okay, and I mean, we wrote this sort of, the two distributions are equal, but the two distributions being equal, I mean, it depends on how you want to say they're equal. Are they exactly the same distribution? In which case we are talking about perfect zero knowledge. But if it is something where the statistical difference is quite small, then you're talking about statistical zero knowledge, though we didn't see any example of this sort. So don't worry about it. But most of the time we'll be dealing about what are called computational zero knowledge, which is you want to somehow say no efficient person will be able to tell apart whether a sample came from here or here. That is, if you think of any small circuit and if you feed it a random sample from here versus a random sample from here, somehow its behavior looks the same. So another way of saying it, a circuit will be fooled into thinking this is actually this distribution. Okay, so it's hard for a circuit to tell apart these two different distributions. Okay, good. So then we saw two examples. The first example is the graph non-isomorphism, or the Coke versus Pepsi test, where I mean the language is the set of all pairs of graphs which happen to be non-isomorphic. Okay, and what was the test? I mean, basically the verifier picks one of the two graphs at random, shuffles it up, shows it to the prover and says, can you identify which graph it is? And then the prover then says, okay, fine, you actually sent me a certain graph. Now, if this identification happens like, I don't know, 10 times in a row, then the verifier can be reasonably sure that, okay, it does seem like the graphs are non-isomorphic because the prover is able to tell apart the two graphs every time I give the prover the one of the two graphs. But I have not learned anything from it. The only thing I'm able to learn from here is that the prover could somehow tell tell the two graphs apart. But I have no clue of how the prover was able to do this. But again, how did we formalize this? We formalized this by giving a simulator. And the simulator just did the following. It basically said, well, just run the simulator, run the verifier V star. So the V star is going to pick a certain bit at random and pick a certain sigma at random and send a particular edge. Okay. But of course, in an accepting view, you accept only if the prover actually returns with the same bit. So those are your yes instances. When you're talking to the honest prover, that's what you would have seen. So you basically say that's the view that I have. Okay. The protocol was really to figure out, does the prover know what B I chose? So that's what the verifier actually talking to the prover is trying to say. But if you're talking to the honest prover and it's a yes instance, well, you will always get back the B that you ended up choosing. But somehow this is something that you could have generated yourself. I mean, these sort of distributions you can generate yourself. So this somehow was to formalize the fact that you're not learning anything from talking to the prover. Okay. Now we
in the simulator definition also, you're not learning anything, right?
Yeah, so that's the whole point, because the simulator doesn't even know the prover. The only thing that the simulator has access to is the verifier.
Yeah.
So the verifier was deviating, and the simulator is like, fine, if you are deviating, I will also deviate exactly the way you are doing. But I'll tell you what would have happened if you had spoken to the prover. And there's no real difference between you talking to me and you talking to the prover. And I clearly don't know whether the graphs are isomorphic or not, because I am in the same boat as you.
What is the upper hand? What is the advantage of doing the simulator thing and stuff?
So the simulator is only to convince the person attending this lecture that this particular interactive protocol did not give any information to the verifier. Okay. And the way it is doing that is saying that, no, you could have gotten exactly what you got by talking to the prover. You could have done this yourself.
Yeah.
So you didn't learn anything from talking to them. Yeah. Okay. Okay. Now let's look at the graph isomorphism part. Now here is a situation where the yes instances is actually isomorphic graphs. Okay. And this was a protocol we saw in the quiz on Academy. And so this is what it is. Here the order is going to be different. It starts off with actually the prover who knows a particular isomorphism between G1 and G2. So he knows if I apply tau, it will transform the graph G1 into the graph G2. Okay. So what the prover does is he first picks a shuffling sigma at random. Okay. Picks a shuffling sigma and now generates this graph H, which is the shuffled version of G2. Say, it doesn't matter whether you start with G1 or G2. Okay. And now he sends H across. And intuitively, it's like saying that, it's like almost telling the verifier, you tell me which graph you want to obtain from H, and I will tell you how to get there. So the verifier now says, okay, fine, show me how to get G1 from H or G2 from H or something. And I will tell you the transformation that would have mapped the corresponding GC into H. But of course, I don't repeat every time the verifier wants to try again, I run this whole thing from scratch so that I choose the sigma again at random, etc., etc. So this is a way of saying that I am fairly confident that, once I send you this H, depending on whether you want to get G1 from it or G2 from it, I will tell you how to get it from it. And the only way I am able to do this is because G1 and G2 are isomorphic. Otherwise, I would not have been able to succeed with this every single time. This was the intuition for this particular protocol. Okay. Good.
Yes.
Yeah.
What is tau?
Oh, tau is a particular isomorphism between that maps G1 to G2. A way of shuffling the vertices of the graph G1 so that you get G2. This is like the witness. This is a witness to say that G1 and G2 are isomorphic. Okay. So this is tau is something that you can imagine the prover already knows. So the prover knows what the isomorphism is, but he's trying to somehow convince the verifier that the graphs are isomorphic without telling the verifier anything about what the isomorphism is. Okay. And again, what is the simulator for this? This is one part where rewinding seem to be necessary. Somehow, I mean, because it's the prover that speaks first, and you somehow want to be able to do this. So what was the verifier? What is the simulator for a verifier V star? So what you do is you first pick this bit B at random. Okay, because you're somehow guessing that this is the challenge that the verifier will ask. Okay, so you pick B at random, and then you pick a sigma at random, and you decide to shuffle just the graph GB. Now notice, as a simulator, if suddenly let's say I had chosen B equal to 2. If someone now asks me, okay, tell me how to get G1 from H, well, I have no idea. I mean, I have no idea whether or not the graphs are even isomorphic. Okay, but if I got lucky and whatever B I chose, if the verifier also asks me, okay, tell me how to get this H from GB, then I'm like, Abba, okay, fine. This is one situation when I can actually give you the answer, so I return sigma. But in a situation when I'm asked the other challenge, then I'm sort of, I can't do much. So the simulator does the following. You first pick a B and you pick a sigma, and you prepare this last response in the hope that the verifier is asking you for GB. Okay, now you simulate the verifier, send the verifier H, and see what the verifier is going to return. The verifier will basically say, okay, now tell me how to get this from GC. If C equal to B, then I return the view. I got lucky. But if C is not equal to B, I'm just going to erase the verifier's memory at this point, start from scratch, and hope that the next time I get it right. Okay. Now notice that basically the verifier is a probabilistic machine or something. Think of something like somebody has given you a C program or a Python program that is doing this job. Now you are just building a different program on top of it, which is going to run the verifier on some while loop or something, but break off whenever C equals B. Now it's just a question of how long is the program expected to run. Now, no matter how the verifier was choosing this bit C, the chance that your original choice of B agrees with C is still going to be half. Right? The verifier could be something like he chooses C equal to 1 with probability 90%. But you would have chosen 1 with probability 50% anyway. So because your choice was independent of the choice of C, the chance that your choice agrees with C is probability half. Which means with probability half, you would have broken out of this loop in a single step. So the expected number of times you will be running through this loop is just 2. It's like 1 by half, which is 2. So that should convince you that this is a simulator that runs an expected polynomial time. And it ends up generating exactly the same distribution as the view of the verifier. Okay. So I think this is what was discussed on the Academy chat. I mean, if there's something that's not clear, I mean, please ping on that and we'll discuss more about it. Is there a question from somebody? Yeah.
Should I ask later on the chat, I guess?
No, you can ask here. I mean, yeah, go ahead.
The simulator wants to verify exactly what the wants to simulate exactly what the verifier would see, and I mean, so the verifier in the actual protocol, if it gets the right permutation pi, then it accepts, but if not, then it rejects, right?
Yeah.
And here it's like the verifier would have sent some random bit, and the simulator sees that, oh, this is not the thing that I expected, so let me try again. But then it will again, the simulator will send another sigma, but the
So the
verifier was
simulator,
not expecting another sigma, right?
no, that's right. But just imagine that you just, I don't know, like an MIB or something, you use one of these deneuralizer and just erase the verifier's memory. Like you are just starting the program from scratch. Okay. And, but I mean, all you want to do at the end of the day is generate a transcript, or rather generate a view. If in the process you're going to repeat this verifier like 30 times or something, you don't care. As long as in some expected polynomial time, I'm able to give you a sample such that the sample is precisely what would have been had you spoken to the honest prover, then that's a way of convincing the verifier that, hey, look, clearly I am a simulator who has no clue of whether or not the graphs are isomorphic. And I'm able to generate the same conversation that you had with the prover. So what could you have possibly learned from that conversation? I mean, yeah, the simulator feels like cheating. I mean, like the verifier prover can't suddenly say no, let's go back from from the start and try again. I mean, the prover doesn't have that option. But here the goal is to just return a transcript. So in that you can sort of freeze your program and decide to make some changes and so on.
Oh.
Yeah.
Yes.
Okay. And we
Just one
saw.
more- I do not know. Possibly said this last class. No. The whole point here is to, if you're not simulating the honest verifiers, this one, it's even to simulate dishonest verifiers is where this is, because
Yeah,
honest
if you want to
verifier,
simulate the honest verifier, you don't need this rewinding at all.
you don't need the rewinding.
I mean, it's just that the stupid verifier could be doing something like, I will look at this graph H, and if H has an odd number of ones, I will ask C equal to 1. Else I will ask C equal to 0 or C equal to 2. I mean, who knows that this verifier V star could be doing completely crazy nonsense like that.
No, it could be just plain malicious in the sense it wants to find out an isomorphism between H and G0.
Yeah. So, I mean, like, and you want to guard against all of them. So your simulator should somehow be able to do, I mean, simulate the view, even if V was trying to be malicious. And that's the reason why often you may, simulators sometimes end up requiring some sort of rewinding type behavior.
Yes. Yeah.
Okay, so that's the reason for this. Okay.
So RP,
Yeah.
if we take some trivial protocol for graph isomorphism where the prover could have just sent the permutation, like this is the reason why they ask. So
Right.
certainly that is not zero knowledge.
That's
But
right.
if tomorrow graph isomorphism falls into P, it will become zero knowledge.
That's right. That is true. I mean, like, because then you can still say whatever you talk to the prover, you could have done all of this yourself.
Yeah.
I mean,
No, that's not clear. That's not clear. It is zero knowledge, because, for example, one way to show primality is by giving out the factorization. Just because primality has fallen in P, doesn't mean that particular protocol was zero knowledge. There's a different protocol that is zero knowledge. It might be that graph isomorphism falls into P by something in which you don't display the graph isomorphism, but you manage to show that two things are isomorphic. But giving out the isomorphism might still be a harder problem than.
No, but this is self-reducible, right? Okay, in some cases it might not be, but for graph isomorphism.
No, it's not. It's not. It's not.
No. So let me try and give you one sort of perverse example for something like this. Let's for the moment assume that we are all babai. We know how to solve graph isomorphism efficiently. Okay, but now the prover could do something crazy. Look, maybe I give you a pair of graphs where there are multiple isomorphisms between them. Okay, but if by some bizarre mean, if you write down this graph's adjacency matrix as zeros and ones, suppose it encodes a formula. Okay, now the prover says, well, if this formula has a satisfying assignment with x1 equal to 0, I will give you this witness. Otherwise, I'll give you the other witness. So here is a way in which the prover, even though the prover is giving a potential isomorphism between G1 and G2, the conversation is somehow revealing maybe a bit more information than the problem required. So whether or not a protocol is zero knowledge is different from whether or not a particular language is already solvable in P or not. I guess that is Prahlad's point. So when we are talking about zero knowledge, we are saying, does this protocol reveal information that the verifier did not already know? And that may, yeah.
But in the case of graph isomorphism, whether you solve it, if you can just get a yes/no language like answer, you will eventually end up finding the permutation also. Right?
That's right. No, but that is only saying that the following protocol, which is the prover says, hey, you know what to do it yourself. That protocol is zero knowledge.
Why is revealing the permutation then not zero knowledge?
No, the point is the prover could reveal something else, right? I mean, revealing the permutation, if all that the prover is doing is maybe revealing the lexicographically smallest permutation.
Yes.
That is zero knowledge, because that is something probably the verifier will be able to do with them.
Yeah,
that is zero knowledge. But I think
it could do something else.
Yeah, making a distinction that a protocol could do something crazy. I was like, yeah, the two graphs are isomorphic, but let me also tell you that this particular number has this as a factor.
Yeah. Okay.
So things like that. Yeah. So okay. Okay. Then we saw that
you need to the thing is in zero knowledge. At least for me, I do not know if this was discussed last time. In the case of soundness, it's very clear. You need to protect the verifier against a cheating prover. That's very clear. Zero knowledge, you need to protect a verifier against, you need to protect the prover against the cheating verifier, and it's a priori unclear why you want to do it. But there are scenarios where you want to, where this makes.
Yeah. So actually, this was one of the quiz questions also. Like there was a honest verifier zero knowledge that we had asked, and is it true that you can always convert one to the other? Anyway, we can discuss that on Academy.
Yeah.
Okay. So one thing I want to point out with this protocol, which is the following, which again was asked in the quiz, but I don't know if I actually haven't seen who all answered the quiz, etc. Which is, suppose you assume that the prover is also some efficient machine like us human machines. No, we can't solve things in p space or anything. I mean, like we are some bounded bounded computation, but somebody has just provided an isomorphism to us. There's nothing more that we know. Notice that that is enough for the honest prover to go through this protocol. Nowhere in this protocol did the prover have to solve some crazy isomorphism problem or anything of that sort. So just this information appeared to be enough for there to be an honest prover here. Now, this is particularly useful when it comes to when we were talking about applications of zero knowledge, and we were saying, no, we are talking about a banking application or something where I don't want the merchant to know anything about my credit card details or something. If I had told you this is something I can do as long as you are p space, you have the ability to do p space. Well, this is not particularly useful in the real world. Because I mean, like, how are we supposed to solve those problems? But here is a brilliant thing where it somehow feels like the prover doesn't need to be too powerful. The soundness is still awesome in the sense that it even guards against super unbounded adversaries and so on. But the honest prover, fortunately here, he only needs to know what this isomorphism is. If you provide this isomorphism to, just a probabilistic polynomial time machine, that's good enough for that machine to actually have this conversation with the verifier. Okay, so this is an important sort of observation. The honest prover is only something like a BPP machine with a witness. You don't need much more than that. Okay, so now let's maybe very briefly go over how did the three coloring protocol work. Okay, the protocol was just this. We assume that the prover knows a valid coloring of this graph G. So the prover is somehow trying to convince the verifier that, hey, the graph G is indeed three colorable. And what does the prover do? The prover picks a random shuffling of the coloring by actually just permuting the three colors, 1, 2, and 3, just permutes the three colors according to some pi. Now commits to the coloring which is pi times sigma. Okay, which is also a valid three coloring, of course, but you put them in some locked boxes and send the locked boxes to the verifier. Now the verifier will say, okay, fine, I want to challenge you on a particular edge ij. So open up those two boxes. I want to see if they have different colors. And the prover says, okay, fine, I'll open those two boxes and basically self-destructs all the other boxes. Okay. And then, but at this point, the verifier probably feels, okay, fine, you got lucky once. I mean, I have a graph on n which has n squared edges. I queried on one edge and you somehow got lucky. Let's repeat the whole thing again. And then the prover will again be like, okay, fine, I'm going to pick another pi. I'll send a new set of locked boxes, etc., etc. And maybe you do this something like 10n squared times. Okay. And we saw that this is a protocol that has completeness 1. Soundness is currently, I don't know, something like 1 over e to the 10 or something, but you can drive it as far down as possible. And it also happens to be zero knowledge or computational zero knowledge. Okay. And the way we sort of formalized what it means to say locked boxes was via what was called a commitment scheme. I just briefly mentioned that there are these things which come from crypto, but a commitment scheme is just a way of the verifier or the prover in this case to commit to a particular value without revealing that value. So commitment is just a function where the prover will choose a key and apply this function to return what is called a commitment. This is the version of a locked box that contains the value. Okay, and it must have two properties. Firstly, once I have committed to a value, I shouldn't be able to change the value later on. Okay, so that's the first part. That's saying if I've committed to a value v1, which means I've sent you this commitment, this C can't be a valid commitment for both v1 and v2. Okay, that's what it means to say it's perfectly binding, that I can't change the value after I have committed to it. And the second thing is computationally hiding, which is that until I open the boxes, the verifier shouldn't know what the contents of the boxes are. Okay, and that is formalized by saying that, well, if you pick this key at random and look at the possible commitment for a string X versus a possible commitment for a string Y, as distributions, they look indistinguishable to me. So I shouldn't really be able to tell apart without knowing what the key is as to whether it came from X or whether it came from Y. So that's what computationally hiding means.
So,
yeah.
I mean, why do you want so? I mean, I would have guessed that perfectly binding would just mean, I mean, it's an injective function basically. That.
Yeah, that's right. That's
but
right.
We are using different keys here.
Yeah. So the point is, so suppose instead this was like computationally binding or something. Suppose I didn't have an injective function here. The reason what could happen is that the prover could commit to a certain commitment, and based on what was asked, the prover can reveal a key in order to fit the, in order to cheat. So because the prover is all powerful, he can search and say, okay, can I give a different key and somehow pretend as if I committed to v2, even though I committed to v1.
Yeah.
So this is to guard against this. Okay. Are there any other questions? Okay. So far, so that basically is like the long recap of what we did last time. So
RP here, the verifier then looks at pi of sigma of I.
I should have mentioned that what the verifier does is he opens box bi and box bj and checks if those two colors are different.
So those colors are supposedly pi sigma I and pi sigma j.
That's right. That's it. That's going to be pi sigma I and pi sigma j. So from the verifier's point of view, the verifier would, if the verifier was talking to an honest prover, the verifier is just going to see two random different colors.
So, okay, got it.
That's the point. That's the reason why this is zero knowledge. Yeah.
But I'm confused about one thing. If suppose there is a malicious verifier and he decides to query I, j, which are not neighbors.
Yeah, that's then, okay.
But then, and he learns that the answers are same. Doesn't he learn something?
No, the prover need not respond at that point of time.
Oh, okay. Oh, maybe I should have said that. Oh, okay. Okay. Actually, that's a very good point. Don't respond.
No, from the prover. So you are only protecting the honest prover against the malicious verifier. You are not protecting every prover against the malicious verifier.
Okay, but the earlier prover was also honest, right? This prover is honest and it does something.
Yeah, no, I that's a very good point. I think I should have changed my protocol to also include this step for the prover. That is, if the verifier is now going to query an I, j, which is not even adjacent, I mean, in the hope that, maybe the verifier discovers that, oh, I and j actually end up having the same color. Okay, I mean, I don't even want to give the verifier that information. So just don't respond in such situations.
Okay.
Yeah, that's a very good point. Yeah. Okay. Okay. In the next about maybe about half an hour or something, what I'll try to tell you is this really cool result of Benor, Goldrake, Goldwasser, Hastad, Kilian, Mikali, and Raghav that says that you can convert any interactive protocol into a computational zero knowledge protocol.
Ramprasad, I'm sorry. In what Siddharth just said, what was breaking when we didn't have that extra step?
So I was always assuming that the ij that was given to me was actually an edge, and therefore the verifier's view is only going to be two random different colors.
Yeah.
But the problem is, suppose this verifier decides to say open box I and box j, and I and j aren't even connected in this graph. Now, this is a way in which the verifier may be able to discover that, oh, there is a coloring that ends up giving vertex I and vertex j the same color.
or different color, or it gets
or different colors, anything. I mean, but the verifier is not supposed to learn this fact at all, because this is new knowledge for the verifier.
I see.
So you do this by somehow forcing this I and j to always be an edge, because the simulator assumed that ij was an edge. I mean, when we proved it, we were somehow assuming that ij was an edge. But Siddharth's point is like, the verifier can choose to give a different I and j, give some complete nonsense. But so you need to somehow make sure that the prover in such situations just doesn't respond.
But like after the end of the process, at the end, verifier can learn a lot of, he can learn the coloring, right? At the end.
No, he can't, right? But the point is, the only
After he opens the boxes, and if he's every time he's picking up an edge from the graph.
No, but every time the prover also chooses a different pi.
Oh, sorry.
That is very, very important.
Yeah,
if the prover didn't choose this pi, then in this 10 n squared whatever repetitions, he can just query all the vertices. He'll learn the coloring. It's very, very crucial that this pi is chosen fresh every time. Yeah. Okay.
No, think of it as this. So think of it as this way. That is, why are you protecting the prover? It seems like a ridiculous thing. Why do you have to protect this prover? It's thing comes from crypto. It's an only cryptographer can come up with this definition. That is, you are going to an ATM and you are entering your details. There you are the prover. You have your password, you have your authentication thing, and that ATM has possibly become malicious. Somebody has put in a thing and it's trying to extract information out of you. So it wants to have a protocol in which it's trying to ask you information. It's saying, oh, through yourself, show me your Aadhaar, show me your this one. You want to make sure that when you're working honestly, you don't reveal information to it. So you are trying to protect the prover, the honest prover who has the information. You want to protect it against a potentially malicious verifier who's trying to grab information out. And that's the whole point. So the moment you realize the protocol deviates, as an honest prover, you're going to stop. If you get an SMS asking you for your password, you're not supposed to respond to it.
Okay. So in the remaining about, the first about 20 minutes or something like this, what I'm going to do is I'm going to give you this protocol in reasonable amount of detail so that we can fill in the other parts. But I leave something in the notes so that, if you want to see, you can go over them and so on. So the protocol, the idea is actually very simple. So you start with the usual protocol. That is, you're starting with some language that you are told has some interactive protocol. And your job is to just blindly try and convert it into zero knowledge interactive protocol. So let's just see, what will that protocol look like? Well, there is a verifier who was talking to a prover. So the verifier probably asks some question. Hey, tell me about Q1. And then the prover says, okay, here is my answer. Then the verifier asks a second question. The prover then replies, here is my second answer, etc., etc. And at the end of it, the verifier says either okay, or the verifier says nice try. Okay. So this is what happens in a protocol. So our job is to somehow make sure that the prover doesn't reveal information. Who knows? The prover could have revealed information in A1, A2, etc. And we somehow want to make sure the prover doesn't reveal information. Okay. So here is a naive way of trying to transform it. So the verifier is going to ask, hey, tell me about Q1. The prover is going to instead encrypt his answer and send that across. And then the verifier then says, okay, tell me about Q2. Well, the prover then again encrypts using a different key and sends that across, etc. So this is what is going to happen. Now the prover is going to continuously talk in some encrypted fashion. Okay, let's give this name. Let's call this alpha 1, which is the encryption of A1, alpha 2, which is the encryption of A2, etc. Okay, so this is what is going to happen. But the point is, there are two obvious issues. Okay, the first issue is, now notice this Q2 was a function that depended possibly on what A1 said. Right? I might be asking my second question based on what I got as an answer for the first question. But now this verifier is basically instead got some garbage, some alpha 1, which is supposed to be, some hidden answer. Now, how the hell is this verifier supposed to now ask the next question? Okay. Okay, like how in general, how is a verifier supposed to ask the question in round I if the verifier has no clue of what was said in the previous rounds? Okay, so that's one obvious issue. The second obvious issue is even at the end of the conversation, okay, you spoke, until this point, and at here the verifier was running a certain function based on all the answers received so far to decide whether to accept or reject. Now here I have no idea what A1, A2, etc. is. Instead, I have only got some encrypted versions, alpha 1, alpha 2, etc. How is the verifier even supposed to know whether to accept this conversation or reject this conversation? Right, so that's the second issue. I mean, like it's like you're talking to someone who's speaking a different language. I mean, like what are you supposed to do at the end of it? Okay, so okay, do people have thoughts on how to solve problem like issue 1? How would you fix issue 1?
With the decrypt thing.
Okay, but then there is no real difference between this conversation and this conversation, right? If at the end of it you're going to decrypt everything, you might as well have not encrypted.
The prover can ask the question also.
Yeah, but again, like that's going to be the difference between NP versus this, right? Because the point is the verifier could have done this using some internal random choices, and even God can't force the verifier to. I mean, God can't do the choices for the verifier.
No, so the verifier in the second round or whatever can reveal their random coins to the prover, which they are, and then the prover will say, okay, this was the Q2 you were supposed to ask.
No, but the verifier's random coins could in principle depend on A1, right?
I don't follow that. So
I mean, in the sense that, I mean, like it may be that
random coins they cannot.
No. So that is, sorry. What I oh, you mean that way? Okay.
Yeah, he's referring to the final solution.
Okay. So okay.
Wait, so what he's saying is that, I mean, the prover can know what the verifier's protocol is. The only thing that prover doesn't know is what the verifier's random bits could have been. The verifier sends it and the prover knows A1, so can run verifiers.
So can the verifier have done that here itself?
Yeah.
Right. And in fact, this we did in the last class, which is just the observation that IP actually equals AM poly. I mean, it can be a completely public coin protocol. And if it's a public coin protocol, there is no reason for the prover to compute the function. The prover can just say, hey, by the way, every message I'm sending is actually just going to be a random string. I'm just going to reveal a random string at every step. And at the end, I will do some computation, I mean, based on what you answer. So the random string could basically be, instead of actually telling you what the question is, I will tell you how I arrived at the question. You are a prover, you are all powerful, you can figure out the question on your own. So I'm just going to reveal to you what my random sequence was. So this is the public coin being super, it's a very useful thing to have. So is this okay? I mean,
does this work against malicious provers?
Yeah. So the whole point of AM poly is that the only thing that Arthur sends at every instance is a random sequence, and it is his public randomness. So in general, IP meant that, Arthur could, I mean, the verifier could have some internal randomness that the verifier has hidden. He doesn't want to reveal to the prover. But one of the things we saw in a couple of lectures ago was the fact that no, there is actually an equivalent protocol where you might as well assume that Arthur reveals all his randomness at every step. And in fact, the only thing he sends is a sequence of random strings. So if Arthur is only talking gibberish,
the sequence of random strings, Q2 is supposed to depend on A1, right? It could depend on A1 as you said, right?
That's right. But the point is, whatever that function was, is a function that the prover knows anyway. So you put the onus on the prover instead. So basically, what was an Arthur Merlin protocol in general? Arthur sends one random sequence, prover replies with something. And Arthur says, okay, fine, but I'll send you another random sequence, completely independent of what has happened so far. Now prover replies something else. At the end of it, Arthur can decide to answer yes or no based on everything that has been revealed so far, like Q1, A1, Q2, A2, etc., and so on. So here
But
also we are basically,
so the A1, right? Even if it knows the random strings, how is it going to?
no, what was Q2 in the Arthur Merlin situation?
It depends on a few random bits, Q1 and A1.
That was in typical IP. I mean, in general, an interactive protocol, the second question could depend on some internal randomness and what has happened so far. But in a public coin protocol, the only thing where Arthur keeps sending are random sequences.
Oh,
Well, at this point, you don't care. I mean, this is some random sequence. It doesn't matter what this is. Your final check will, of course, involve everything. We have not yet come there yet. But I'm just saying, as far as this message is concerned, it's a sequence of random strings.
okay.
So, I mean, like, so the point is, if it's like, if Arthur is talking gibberish, it doesn't matter if he's talking to a person speaking Korean. I mean, even if he doesn't understand what has happened so far, he can still continue to talk gibberish. So Arthur doesn't need.
By the way, it's not IP equals AM poly that you need. You need Goldwasser subset.
Oh, I thought that was all part of this, or no?
No. If it were a constant round IP, you want to say there's a constant round AM. You don't want to make it a polynomial round AM.
No, I don't care. I mean, all I want to say is, I mean, here I don't care if the number of rounds increases.
Okay, fair enough. Okay, because the proof you'll be showing is a stronger proof. You'll show if something had a constant round IP, it will has a constant round.
Maybe. Yeah. So Arthur doesn't need to understand previous messages to send a random string. Okay, is at least issue 1 clear? I mean, we have, the only thing we have done is move the problem from one place to another place. I mean, we still need to figure out how the hell is Arthur going to decide whether to accept or reject. We just said at this point you don't need to know any further, but we'll try to solve the problem here. Okay, now how the hell will the verifier know whether to accept or reject? Now here we may assume that there was some function, some verify of Q1, A1, Q2, A2, blah, 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 which decided whether or not the verifier is accepting or rejecting. Now I want to compute the same function, except I don't know what A1, A2, etc. are. Instead, I only have these alpha 1, alpha 2 and stuff like that. Now, how is the verifier supposed to figure out whether to accept or reject?
Can it ask the prover about something? And
yeah, so one of the things it can, so what is one thing it can ask the prover to help it decide whether or not to accept or reject?
what is the corresponding answer to alpha is?
Yeah, so one thing it could be like, at this point, the verifier could say, hey, by the way, can you give me the keys K1, K2 all the way till Km so that I can figure out what A1, A2 are and then decide to accept or reject. So one possibility is to ask prover for keys. But this defeats the entire purpose because the whole point of doing the encryption was to make sure that you don't reveal A1 through AM. So now what's the point of asking for the keys? Okay. And here is the next cool thing, which is to look from the perspective of the prover and say, what does the prover now want to know? The prover wants to, or rather, what does the prover want to convey to the verifier? The prover wants to convey to the verifier that here is a set of keys that if I had sent to you, it would have made you accept. Right? I want to basically say I have valid decryption keys with me that had I sent you those decryption keys, you would have run this particular function to figure out that it is actually an accepting configuration. But I don't want to send you the keys. So let's just slightly rephrase this to say that there exists keys K1 blah 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 till Km that I could have sent to you such that this verify process of Q1 A1 blah 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 till Qm Am. But what are these AIs? Where AI equals whatever the decryption function of Ki with alpha I.
This is an NP, right?
That's right. That's the second cool fact, which is that at this point, the prover wants to convince the verifier that this NP statement is true. Okay, and the prover doesn't want to actually send K1 to KM in order to convince the verifier that yes, you would have accepted had I sent you these keys, because that will reveal too much information. And the key observation here is that this is in NP. Okay, so you can actually run the GMW protocol here. So I mean, okay, this might, I mean, it's like, it's two simple ideas, but it's like super clever ideas. I mean, the first step was basically just doing nothing. I mean, it's like saying that the verifier is just asking random strings, so it doesn't matter if the verifier didn't understand what happened earlier. So let's just convert the protocol to an AM protocol and move on. Now it's the second part which is super, I mean, it's really clever, which is to say at this point, what is the prover trying to make the verifier do? The prover wants to tell the verifier that had I given you the correct decryption keys, it would have made you correctly figure out that, you know, the answers are something that make you accept. Now this is a polynomial time computation, this is a polynomial time computation. The only thing is there exists in front of it. And therefore, this entire string can be encoded into, I don't know, some graph G, such that this graph G is 3 colorable if and only if there exists K1 through Km, that makes this entire formula true. This is just using the Cook-Levin reduction and saying that 3 coloring is an NP complete problem. So now at this point, the prover will just try and convince you that this G is 3 colorable. And notice that G is something that both the prover and the verifier can build themselves. Because in order to build the graph, you only need to know what this formula phi is. And now the prover is trying to say that the formula phi was satisfiable, which is the same thing as saying the graph G is 3 colorable. And so that is something that the prover can do. It's a really cool this thing. So okay, so here is a full proof. I don't want to go too much into it. There's a bunch of things you need to assume just to make sure the proof works. You first assume that the IP protocol that was given to you was an AM poly protocol. That is, it is public coins. The verifier only keeps sending random bits, and you assume that the acceptance thing of the verifier is deterministic. The prover is also deterministic. Some minor things, and there is one point where you'll also need to assume that the protocol has perfect completeness. But these are all things without loss of generality, because we saw this in 2 lectures ago that you can take any IP protocol and make sure that these properties hold. And completeness and soundness is straightforward. The only thing is zero knowledge part, and here is the simulator for the zero knowledge part. It's okay. I mean, I think I'm bombarding you with too much information, but I leave this in the notes. So if there is something that is unsure of, you can go over the notes. If you have doubts, I mean, ask on Academy and I'll try to answer. Okay. So at least I hope this was a non-zero knowledge proof that this whatever this BGG-HKMR protocol. Yeah, it's a really nice. It's a really cool proof.
How did so many authors get into this?
I have no idea.
This happened at a cafe, possibly. People just.
Yeah. Okay. Cool.
Yeah. I had one more question. Yeah. So can we, like in this protocol for 3 coloring, can we make it perfect zero knowledge, or that is something not possible? Or?
No, it's not expected to be perfect zero.
Yeah, I know it is not expected, but I don't know why it is the case.
No. So even if you can make it statistical zero knowledge, it will fall fairly low in the hierarchy. Statistical zero knowledge falls in AM. So a co-NP problem will, if it has AM, we know the hierarchy collapses.
Oh, I see. Okay. So it's not, I mean, these protocols are not expected to become statistical or even perfect. I mean, perfect or even statistical zero knowledge.
Okay.
Yeah. Okay. Cool. So that was all I wanted to say about the protocol for IP. Okay. Now let's move on to the next, small concept, and This is called this proofs of knowledge thing. I'm not going to go too much into the detail. I think this sort of, this goes pretty deep into crypto. But I do want to mention this because it's a concept that feels like, yeah, this is something I would like to capture, but it's very hard to come up with the right definition. Okay, so let's go back to, I think the best way to describe it is one of these other protocols. Okay, so let's take the, just for simplicity, let's take the 3 coloring protocol. Okay, what does this protocol say? It says that if the graph is 3 colorable, then there is an honest prover that makes me accept with probability 1. But if the graph is not 3 colorable, then no dishonest prover, I mean, even if it's a dishonest prover, no prover will be able to make the verifier accept with, let's say, probability bigger than 1/3 or something. Okay, but okay, now suppose let's say we are working with a yes instance. Okay, the graph is indeed 3 colorable. Now the only guarantee from completeness is that the honest prover will make me succeed with probability 1. But now suppose a prover comes along and makes me accept with probability 75%. This is still a pretty high number. Okay, now can I be convinced that, oh, the only reason this guy is able to convince me so well is because the guy knows a 3 coloring? That's the sort of statement I want to make. Okay, so let's go back, let's go to the what this is. And the proof of knowledge is a way by which a prover is trying to convince the verifier that the prover is in possession of a witness. Okay, and these are instances when the verifier doesn't want to know whether or not the graph is 3 colorable. The verifier is more interested in knowing, do you know a coloring for this or not? It's a subtle difference, but it's an important difference, right? I mean, it's like one of these things where, if you have a password prompt, okay, let's say that TIFR, every person is given some composite number, and your identity is the fact that this composite number is a product of 2 primes. Okay, maybe that's what TIFR does for each of our keys or something. But there is no point in someone coming and telling me, hey, I can tell you that this is a composite number. Well, that's like, duh. I mean, I don't care whether this is a composite number or not. What I want to know is, do you know what the factors are? So it's a slightly different concept than just telling somebody whether or not a certain fact is true. Now you're asking, does someone have possession of a witness here? Now, how do you formalize something of this sort? I mean, I want to make a statement that's something of the sort that if, or let me write it as, the only way this prover can convince me with high probability is if the prover knows a witness. So soundness is already telling us that if there is a prover that makes the verifier convince with high probability, then the statement is true. But it is not saying if provers who manage to convince the verifier are provers who know a witness. And that's the subtle difference. Okay, and it's sort of hard to describe without actually trying out a few examples. Okay, so let's try an example of one such NP zero knowledge protocol. And again, the simplest I think is the graph isomorphism protocol. Okay, what was the protocol here? So there was a prover who sort of knows a particular tau that was a transformation of the graph G1 to the graph G2. So this is what the prover knows. So what did the prover do? The prover chose a sigma at random from Sn and set h to be equal to, I don't know, sigma of G2. Okay, and sends h across to the prover, sorry, to the verifier. Now at this point, the verifier says, okay, fine, I'm going to challenge you and I want you to tell me, how did you get h from G1 or how did you get h from G2? That's what I want to know. So the verifier is going to choose a bit b at random, which is either 1 or 2, and basically ask the prover, okay, tell me how do you get this from graph GB? Okay, And now at this point, he says, if b is equal to 1, then you set pi to be equal to, what do I need to do? Sigma and tau. Okay, and if b is equal to 2, you set pi to be equal to sigma. And then you send pi here. Okay, now you check if this h was equal to pi of gb. And then you return either okay or nice try. Okay. So this was a protocol that we just saw of graph isomorphism. Now, okay, so this basically, what did we learn from this protocol? We said that if the graphs were non-isomorphic, then no matter how awesome the prover is, the chance of the prover succeeding is just half. It can't be any more than half. But on the other hand, if the graphs were isomorphic, we want to say there is an honest prover who will make me succeed with probability 1. But we want to now ask a finer question, which is, suppose P star makes verifier accept with probability, I don't know, let's say 3/4. If that were the case, you already know this is a yes instance, just because of the fact that soundness tells you that if it's a no instance, no prover would have made the verifier accept with probability more than half. So you are in the yes instance right now. But if you made the verifier accept with probability 3/4, does it mean P star knows an isomorphism? And intuitively, the answer feels like the answer to this should be yes. I mean, how else is a person supposed to, succeed with this protocol 3/4 of the time without knowing an isomorphism? I mean, it feels like intuitively the gut feeling is that the answer should be yes, but the point is I don't know how to formalize this. Okay, right? How do you write down the fact that what does it mean to say the prover knows something? Okay, and Bellare and Goldreich, they formalized, though this notion of proof of knowledge was there earlier, the final fixed proof was given by Bellare and Goldreich, and it was intuitively saying that you should be able to extract a witness from such a prover. That is, you give me any prover that happens to make the verifier accept with this high probability, and using that prover, I will generate a witness. Okay, so, and it's a slightly weird way of saying this, and this is often called what is called a knowledge extractor. Okay, so let's see an example, and then it'll hopefully become clear to you as to why this is a cool definition. So here is what a knowledge extractor's definition is. Okay, a knowledge extractor is basically a randomized, I mean, it's similar to the simulator machine. It's an expected polynomial time machine which may toss random coins in the process, which has been given access to this surprisingly good prover who's managing to make the verifier accept with high probability. Okay, and there's a slight thing, I need rewindable black box access to this prover. That is, just imagine somebody gave you a source code that says this is what the prover is doing. The prover internally could do all sorts of crazy things. I don't care, but it's a source code where I have a pause button and I have a save state button. It's like as if you can just freeze that laptop and say, I want to save the state of that laptop and go back to that. So you have this miraculous Oracle access to this prover. And this prover is promised to somehow make the verifier accept with high probability much larger than a certain threshold. In which case, in this graph isomorphism situation, we were taking the threshold to be half. And we were basically saying that there is some prover that accepts with probability like 3/4 or something. I want to say, given such an access, I mean, given such a prover, I should be able to produce a witness in expected polynomial. That is like saying that, whatever I am doing as a knowledge extractor is something, had the prover done it on himself, he would have extracted out a witness. So in principle, the prover knew a witness. That's the only reason he was able to convince the verifier with high probability. Does this, yeah?
Arpi, what is the difference between a knowledge extractor and a simulator?
So here the simulator usually has access only to the verifier, not with the prover. A knowledge extractor is something that's saying you are taking a prover who is managing to make the verifier accept with high probability and somehow extract out a witness from it. The simulator's job was to actually produce a sample of a transcript. But here, this guy's job is to actually produce a valid witness for the yes instance.
So in some sense, a knowledge extractor is sort of a strengthening of this usual. If you had an algorithm that solves SAT, from that algorithm, you can pull out the satisfying assignment. This is what it is trying to say. If you had a prover that could convince me with high probability, I could use that prover to actually pull out the witness from the provers.
That's right.
Oh.
So
but maybe I'm getting confused. So what I'm getting confused with is, on the one hand, this protocol for graph isomorphism was zero knowledge. And we are also extracting.
So the final thing that I want to say is that this protocol that we saw here is actually a zero knowledge proof of knowledge. It's not just trying to convince the verifier that the two graphs are isomorphic. It actually further convinces the verifier that if there is a prover that succeeds with probability much bigger than half, then it must be the case that the prover actually knows a isomorphism. So it's doing more than just convincing the verifier that that the graphs are isomorphic.
Ramprasad, can you go back to the definition of knowledge extractor? What is this rewritable? I mean, I can see that somehow you want a definition, which it shouldn't allow a verifier to become a knowledge extractor, right? Needs to be powerful.
That's right. So the verifier doesn't have an option of telling the prover, hey, let's rewind to step 1. The prover will be like a nice try. I mean, I chose my randomness or something. Now you can't ask me to rewind. But I'm saying if somebody gave but the prover can do this themselves, right? At the moment, the prover may say, hey, no, I have a weird way in which I'm able to convince a verifier, but I don't know a protocol. But then this is a way by which saying, no, I'll tell you how to extract a witness from whatever you are doing. So you were doing something now. Okay, what would you have answered if this was the question? And then I ask, okay, what would you have answered if something else was the question? And if you're able to give legitimate answers, I'll tell you, with these two, you can actually pull out an assignment on yourself. So it's a way of the knowledge extractor is trying to convince the prover that no, whatever you're doing, you somehow think you don't know the witness, but you actually do. So
M can't be a malicious verifier. M cannot syntactically match a malicious verifier.
M can, but the
there's no this rewindable.
So okay, or maybe I'll give you an example, and maybe we can see how exactly this knowledge extractor works for graph isomorphism, and maybe we'll revisit these questions if the questions still persist.
Can I give an example of something which is not a proof of knowledge? For example,
please.
So you run these sort of, when you do these credit card transformations, sometimes some of your credit cards have these grids at the back of your card. They have this A1, and sometimes instead of sending you an OTP, people ask you, give me the number in the grid position A1, B3, C5. And you have to give these numbers. This is why is this being done? Because the verifier wants to ensure that the prover, prover in this case, the owner of the card, actually has the card in their hands. You want to check this. So I want to now say that, so this is to check that you actually have the card. That is, you have the witness in your hand. This is to check that you have the witness in your hand. The card is in your hands, and hence you are able to do. But this does not prove to you the card you have in the hand. It only proves to you that what you have is, you can run it on the entire grid by doing this rewindable black box access and get the whole grid for this one. It only proves to you that you have this grid thing with you. It doesn't prove to you that you are the owner of the card. So somehow you want to say the witness is not just the card, the witness is This is one way of stating you have something of the card. You want to, this is this one, you want to actually show that the person has the card. Depending on if the card is the grid, then of course this rewindable thing, you keep on running it for every question in the grid, you get the entire grid and you know that the person has the card. This is not zero knowledge by any way, but this is a proof that that the other person has the card in their hand.
I didn't follow it, but
why don't you use one?
I mean, I'm not.
It is not zero knowledge. These are two different things. Proof of knowledge and zero knowledge are two different objects. It so happens that the graph isomorphism has both of them.
No, but what was your example illustrating?
So what does this knowledge extract? So why is this protocol done? This protocol is done.
No. So actually, before, so the asking for the grid, are you saying it is not a proof of knowledge, or are you saying
depending what do you mean by knowledge here? Is knowledge is the witness over there the possession of the grid or the possession of the card? If it's possession of the grid, certainly it is proof of knowledge, because you can keep going back and forth and ask the entire grid and eventually show that, yeah, this guy would have accepted. If it is possession of the card, it does not. It only proves to you that you have this part of the card. It doesn't prove you that you have the card with you, because the card has other information hidden on it, which you're not revealing. This is sort of trying to convince to you that the person, it is a proof. It is sort of an ad hoc thing for proof of knowledge. It is to check that the person who has it has the card. It is in spirit very much similar to this. But all it checks is the person who has access to the grid. It doesn't prove that it has access to the card. Whereas the protocol which we are going to give is going to give a stronger thing. It will say it actually has access to the entire card. The entire witness should be there. You will get it out of. For graph isomorphism, we'll be able to show that. For example, SAT, we are able to show it. SAT, if you have an algorithm for SAT, if you didn't care for zero knowledge, SAT, the usual algorithm for SAT, you can use that algorithm for SAT to extract out the assignment. So it's a proof of knowledge.
Okay, I don't want to get sidetracked. I still feel I don't follow. Okay. So here's what I want to do. I want to first give you the knowledge extractor for the graph isomorphism protocol. It'll really feel like cheating, but I want to convince you that this is still a non-trivial definition. Okay, so here's what the knowledge extractor is going to do. Okay, I'm going to first run p star. So the protocol actually starts off with the first message is actually sent by the prover. Right, in graph isomorphism, the first message is a shuffled version of one of the graphs that the prover is sending. Okay, so let's first run p star to get the first message h. Okay, now what I'm going to do is I'm going to save the state. Okay, it's like as if I just take a copy of the messages. I mean, like the prover has some program, it was run on some machine, I'm just going to freeze that state. Okay, it's like as if, let's say there is a prover who says, hey, I can somehow manage to make the verifier accept. And it's like saying, okay, fine, the knowledge extractor is doing the following. Okay, fine, tell me your first message. Okay, the prover then says, okay, no, my first message would have been h. And now the knowledge extractor asks, send b equal to 1 and get pi1 from p star. This is like asking the knowledge extractor is asking the prover, had the verifier asked you b equal to 1, what would you have responded? And the prover says, well, I would have responded with pi1. Okay, now this is like where you rewind to saved state and ask, had the verifier sent you b equal to 2, what would you have responded? And then the prover says, well, I would have responded with pi2. Okay, and now what is a candidate witness that you have? Well, if the prover is saying that pi1 is the way to go from g1 to h and pi2 is the way to go from g2 to h, then if I want to go from g1 to g2, I mean, all I need to do is basically, what is this, pi1 pi2 inverse or something? That's what I need to do. Okay, but again, the prover didn't make the verifier accept all the time. So currently this pi1, pi2 inverse pi1 is just your candidate isomorphism from G1 to G2. So what you do is, okay, maybe I should have written it this way. Check if pi1 this of G1 equal to G2. If yes, return this. Else, retry. And this is the knowledge extractor. Obviously, the verifier can't have this conversation with the prover, because after the prover has sent an answer, the verifier can't say, had I sent you b equal to 2, what would your answer have been? The prover will be like, nice try, let's start from the scratch. I'm not rewinding on your this thing. But think of the knowledge extractor as someone having a conversation with this prover and saying, you somehow think you don't know an assignment. But I'm trying to tell you that no, you actually do know an assignment. It's somehow internally present in your code. And this is a way of somehow extracting that for the prover.
RP. So
Yeah.
if you have a zero knowledge protocol, and you want to design a knowledge extractor also, this M, then it must necessarily use this rewinding access, right?
That's
Otherwise,
right.
it will just become,
Actually, I don't know how to formally say this, but it feels like if not, then the verifier could have been able to do the same thing.
Yeah.
So you can formally show it. No, otherwise the verifier, the problem goes into BPP, because
yeah, it feels like, I mean, like the only reason the extractor seems to have some extra power compared to the verifier is the fact that the extractor has the ability to get the prover to rewind to a state and ask, what would you have said had the question been this? I mean, there's no reason for the prover to entertain such things by the verifier.
Yes.
Okay. So of course, this is right now, we have just written a knowledge extractor. One thing we should convince ourselves is, why is this expected to run in polynomial time? Because I mean, whenever you have a while loop that is going on forever, you should always be scared of this. Like, how many times will you keep retrying? Okay, and you should, and it's not like I know that this prover is going to succeed with probability 1. All I know is that it's like succeeding with probability something like, I don't know, 3/4 or something. I mean, is that something that's good enough? Okay, and here is a good way to describe what exactly is happening. What's the intuition? Why would you think this should work? Okay, now let's just look at this protocol tree, like the way we had defined a while back, to sort of argue what is the probability that the prover makes the verifier accept. So these are all possible first messages that the prover could have sent. Maybe the prover is sending some weird distribution of first messages. Now, based on whatever was sent, the verifier may now ask one of two possible challenges, maybe b equal to 1 or b equal to 2. And then at this point, maybe the prover could respond with a whole bunch of messages. I mean, the different messages the prover could say. What do we know from this entire thing? We know the probability that this protocol ends up the verifier accepting is at least 3/4. Intuitively, that means that there must be a substantial number of these H's where on both challenges, the prover makes the verifier accept. Because if in every such thing, only one of them was actually, the prover was only right on one of them, then the overall success probability of the prover could not have been more than half. So intuitively, that's the reason why you believe there should be a pretty good chance that many of these H's actually have both of these things being good from the prover's perspective. That is, it somehow makes the verifier accept. Okay, and that's what we want to formalize. We want to somehow say, therefore, if you basically ask the prover, what would your first message have been? It's very likely that the prover answers something where he would have correctly answered for both b equal to 1 and b equal to 2. And therefore, there is a decent chance that you will exit out of this loop, in few steps. That's the rough intuition as to why you think that the knowledge extractor should run an expected polytime. Okay, now let's try and formalize this. We'll say that one of the possible answers of the prover, the first answer of the prover, is good. Okay, if after the prover commits to that answer, okay, P star makes verifier accept with probability, verifier accept after saying H, I want this probability to be at least, let's say 2/3. Okay, so it might be the case that some of these H's, both, I mean, there is a decent chance of you making the verifier accept. Overall, I know the probability is at least 3/4, but I'll call a particular first message as good if this probability is at least 2/3. Is the definition for what a good first message is clear? I mean, we are somehow assuming that the P star had already committed to H. Now the protocol only means the verifier sends a message, the prover sends a response. Now, what's the chance that the verifier ends up accepting? If that is bigger than 2/3, I will call such an H as good. If that is not bigger than 2/3, I'm going to call it bad. Okay. So now what I want to say is that I want to say there is a decent probability that the prover's first message is good. Now, why is this true? So let's say I'm going to put all these possible first messages into a straight line and say, these are my good messages and these are my bad messages. Some fraction of these first messages may be good, some fraction of them may be bad. I am somehow trying to argue that a good fraction of them are good messages. Okay, I'm just using the same word too many times. Okay, but now let's ask ourselves the following. Let's say that there is a delta fraction of them which are good and 1 minus delta which is bad. I'm trying to figure out what is this delta going to be like. Okay, now I want to ask, suppose the prover decided to give a good message. What's the largest probability that the verifier will end up accepting? Currently, we are saying it is at least half, but I want an upper bound. So let's say the verifier accepts with probability at most 1. I mean, it's a probability distribution anyway, so the probability of the verifier accepting is 1. But on the other hand, if the prover started off with a bad message, what's the probability that the verifier will end up accepting? What's the largest that this can be? So here we basically said we'll call something as good if the probability of the verifier accepting was at least 2/3. Which means if you're looking at bad assignments, then this is at most 2/3. 2/3 will be the largest probability that the verifier may accept. I mean, if it was bigger than 2/3, I will have put that in good anyway. Right? I mean, just by the definition of what good and bad means. So therefore, the chance of the verifier accepting here is at most 2/3. So overall, what's the largest probability that the verifier will be accepting if the protocol is run? Well, there is a delta chance of the prover giving you a good message. And in such instances, there is a probability 1 of accepting at most. And there is a 1 minus delta chance of starting with a bad message. In such instances, you accept with probability at most 2/3. So overall, it's going to be delta times 1 plus 1 minus delta times 2/3. Right? Which is, what is this going to be? This is going to be delta by 3 plus 2 delta by, 2 by 3. But I'm assuming that the verifier accepts with probability bigger than 3/4. I'm only interested in provers that happen to succeed with that higher probability. So I know for a fact that this better be bigger than 3/4. Okay, and this basically will force you to say that this delta is at least 1/4. Is that okay? So I don't know. This is often called what is called an averaging argument. That basically is a way of somehow indicating to you that, well, you know that overall over the choice of your first message also, you have a 3/4 chance of accepting. And you somehow want to say that on average, even when I fix the first message, I should have a pretty decent chance of accepting. So, okay. Don't know how many of you here like follow this proof so far right now, but at least this is, I mean, hopefully the message, I mean, the statement is at least believable. Why did I erase that?
Did somewhere this 2/3 become 3/4 or?
No. So we are assuming that P star succeeds with probability 3/4.
P star succeeds.
So
Okay.
that is, I should have written something here. I want to say P star succeeds with probability at least 3/4. And I want to argue that from such P stars, I can extract out a witness.
So the lemma has threshold half. So it can't
so
be half. No, it should be half plus delta for some
generally
delta.
threshold means that, if you are much bigger than threshold, you should be able to extract out a witness. And I'm just illustrating that much bigger than 3/2 to basically mean 3/4. Otherwise, there'll be some extra parameters that will float in throughout. I'm not bothering too much about it. Okay. Good. So this basically says that the first message is good with some decent probability. I'll probably take another just 5 minutes or something and be done.
And here the only thing you're using is 2/3 is less than 3/4.
That's right. That's the only thing I'm using. I just chose 2/3 because it's a little less than 3/4. That's it. Okay. So now let's ask the following. Let's fix a good message H. And let's say P is the probability that verifier accepts after the prover sends an H and the verifier sends B equal to 1. Okay. Let's say, what is the chance? I mean, this is like saying, what is the chance of the prover succeeding here? I'm going to call that P. Prover succeeding here, I'm going to call that Q. Okay. And Q is the probability that verifier accepts after H and 2. Okay. What do I know right now? I know that P plus Q by 2, this is at least 2/3. Because we basically said that H is a good first message, which means there was a 2/3 chance of you accepting. So there's a probability half of you going into this situation versus this situation. So there is a P by 2 chance of you accepting in this situation. There's a Q by 2 chance of you accepting in this situation. Okay, this is what we know. So what does this mean? This means that P plus Q, this is at least 4/3. Now P and Q are probabilities. Okay, so the largest value that P and Q can take is at most 1, which means if their sum is bigger than 4/3, it better be the case that the smaller of the two is at least as large as 1/3. I mean, in order for you to reach something like 4/3, you can't have any of, if Q was smaller than 1/3, then it will force P to be bigger than 1, which is of course not possible. Okay, so this basically means that both P and Q are at least 1/3. So far, so good. What does this mean? This means, what is the probability that verifier accepts after H1 and H2? This must be at least 1/9, right? Because this is like saying there is a 1/3 chance of this guy accepting here. There's a 1/3 chance of this guy accepting here. So here this guy is asking, okay, you happen to find the first message. What's the chance that both this one and this one, you actually give the right answers? That is, you give answers that make the verifier accept. The probability of this happening is 1/3. The probability of this happening is 1/3. So overall, the probability of both of them happening is going to be 1/9 at least. So this basically says that the probability that this knowledge extractor will get out of this loop right in one step is, there was a, I don't know, what was this? There was a 1/4 chance that the first message is good. And then there is a 1/9 chance that both of these result in the right, make the verifier accept. So this together will basically mean that this implies that M breaks out of loop with probability at least 1/36 or something, which means on expectation, the number of repeats is going to be like 36 of them. So you now have an expected polynomial time algorithm that happens to extract out a witness. Okay, I mean, probably a bit confusing the first time you're seeing it, but hopefully, I mean, don't worry too much about it. There's actually a protocol for Hamiltonicity, which I unfortunately erased. Let me just try and put it back one sec. Okay, we're just going to cut and paste from this. Paste. Let me just go back here and paste. Yeah. So, I mean, since we did this for graph isomorphism, your natural thing might be, can I do this for all of NP? Can we have proofs of knowledge for any language in NP? And turns out you can. And Blum gave a protocol, zero knowledge protocol for Hamiltonicity, which actually happens to be a proof of knowledge also. Okay, so I'll just write this here. I'm not going to go through what the protocol is. I mean, you can check the notes and go over it. And for those of you who may be interested in learning more about this in general, these sort of protocols are in general called sigma protocols because of the shape that these protocols are in. I mean, looks like a sigma, I guess. So it's a protocol that basically has a template that looks like the prover commits to something, verifier sends a challenge, prover sends a response. So a lot of zero knowledge protocols actually take this particular shape, and sigma protocols are like built on top of that with some extra conditions or something. And there's a really nice sort of article by Ivan Damgaard called on sigma protocols, which actually goes through this in detail. And those of you who want to read more about it can read up more about this and so on. There are also this completely crazy things in crypto which are called non-interactive zero knowledge proofs, which, I mean, it just looks mad that something like this is even possible. But there are these things called NIZICs. I mean, that's what non-interactive zero knowledge is called. And there are these NIZIC proofs for things and so on. And if you are interested in crypto or things like that, these are topics that you may want to encounter. Okay, I'll stop here. I've already gone well over time. So I'll just take questions and stop otherwise.
So
Yeah.
RP, in the proof we just did, the previous proof, here, like the probability that we will accept when H, if our B is 1, that is, we can define this event that, okay, what are all these possible H's which lead to acceptance when B is 1?
When B equals 1, okay.
And similarly when B equals 2. So one is, let's say one probability is P, one probability is Q. Then you get that P plus Q by 2 is exactly 3/4.
That's right.
So you are just saying that these two events must intersect. And if they intersect, you will exit the loop.
No, I want to say they must intersect often enough.
But they intersect at least half, right? They are
yeah, in this case, yeah, they intersected. Oh, I could have just done that instead. Oh, you're saying rather than condition over the possible choice of the first message. Is your point that I needn't have done that at all?
Yeah, that is, I'm trying to say, maybe that also works. Maybe that is, you can just.
What?
So Siddharth's point is, let's just look at what is the probability that you would have accepted when B equals 1. I mean, that is, collect the probability from this together. That is some probability. Let's call that P. Now, what's the probability that you would have accepted in B equal to 2? All of these guys. And let's say that is Q.
Yeah.
So you know that P plus Q is at least 3/4 because you're assuming that the prover succeeds with probability bigger than 3/4.
Yes.
So this already means that many of these H's must have both this and this being true reasonably often.
Yeah.
So maybe there's a different calculation that doesn't have to be as complicated as I did it.
It's the same thing, no?
Maybe it's the same thing. I mean, this was just something that I worked out yesterday. So, I mean, it's probably not the optimal way of doing things. Yeah, but it's sort of important that, if your P star just succeeds with probability half, this proof will just fail because you will get to a point where you get P plus Q by 2 is at least 1. And then you're stuck.
Yeah, there's no intersection.
Then this is no intersection. You can't do anything with it. So which is why you can't extract the knowledge from a prover that just barely succeeds with probability half. But the moment you start crossing half, the farther away you are from half, the number of repetitions becomes smaller.
It's also pretty interesting that prover who doesn't know anything can't even fail with probability smaller than half. It's difficult to also fail with probability smaller than half.
Oh, fail with probability smaller than half.
Sorry, fail with probability larger than half. So that's what I meant. That is
No. So I mean, but if the prover can do something silly, right? I mean, like, I mean, the verifier asks the question and you just say blah, 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 or something. I mean, just basically don't give any answer.
right, wait.
I mean, just fail in some obvious way. I mean, yeah. Yeah. Anyway.
Okay. Sorry,
Okay. We'll
It's an
stop here.
isomorphism in to a completely different graph.
Sure. I mean, you're talking about two n vertex graphs and you give a 42 vertex graph and say, yeah, this graph is nice or something. Yeah. Anyway, I'm
okay,
just saying things that we all agree on just for fun. Yeah. All right. Okay. So then let's stop and we'll continue. We'll start a new topic from Wednesday onwards. We'll be doing PCPs. Prahlad will start.